Good afternoon, students. I am Dr. Sudarshan Behra, working as an assistant professor in CSE in the School of Computer Science and Artificial Intelligence in SR University, Warangal, India. In the last class, we discussed how different phases of a compiler works. I mean, how individual phases of compiler work. And we realized that with the help of an example. We took a single example and we observe what is the role of each and every phase of the compiler through that single example, right? So more or less, we came to know what is compiler, what are the different phases of compiler, and how each and every phase of compiler works in order to convert the higher level language into the machine code. Right? I hope this thing is clear to you. More or less, it is clear to you. Okay. Now we'll navigate in depth to each and every phase of the compiler. Okay. So that we can have a clear, clear idea how different phases works together. Okay. In order to complete or in order to convert or translate the entire source code written in high level language to the machine. Okay, I think this lecture is 4. Lecture number is 4. Okay, here onwards we will be discussing unit 2, which completely holds two pages of the compiler. One is lexical analyzer and second one is syntax. Okay. So here you can see the heading is unit 2 and the first phase of the compiler that is called as lexical analyzer. Okay. Now let us review once again, as we already discussed more or less. Okay, what is the role of lexical analyzer? It is, let us take one more review on that. Okay, before we navigate in depth to the actual function. Okay, I mean actual in the sense what? In depth, before we analyze the in depth working principle of lexical analyzer. Okay. So as I said before, the lexical analyzer is the first phase of the compiler. It reads the source program character by character. Remember once again, it reads the source program character by character, and it groups the characters into a meaningful word called as lexeme. And for that lexeme, it find out the corresponding token type of that lexeme. That is the major role of lexical analyzer. Okay, and simultaneously it removes any comments associated with the program. Sometimes we are writing comments, no hashtag comments. We are using hashtag to write comment. Okay, particularly in C and C++ language. Okay, that comments are never going to be executed. Okay, comments not execute. Okay, so that is why these comments are not actually considered as the part of the program. So here, while scanning the program, while reading the program, okay, from the starting to the last, whatever the comments or white space are encountered by the lexical analyzer, it just skip them or it just remove them. Okay, because these are not the tokens and they are not going to execute in the program. They are not a part of the code. For our convenience, for our understanding, or what we are writing, somebody else can understand it easily. Okay, for that purpose, we normally put some comments. Okay, so this is so and this is that, this is so and so and this is that, like that. Comments we need to add. Okay, for our convenience, but those comments never execute. Okay. Similarly, within the programming construct, if any white space is encountered in between two words, if white space is encountered, that white space also eliminated. I mean, the lexical analyzers keep the white space and it then go to the next word. Once it is scanned one word, it will go to the next one. So here is one example. You can see the example is written in C language. Sum equals to a plus 10. So sum is nothing but an identifier. Here equal symbol is an operator. A is an identifier. Plus is an operator. And 10 is a constant. Then the line is terminated by semicolon. Okay. So let us assume that lexical analyzer it reads this particular line. Then what it does, it convert. Okay, sum, SUM, sum is a single word. Okay, once it encounters this word sum, okay, then it find out the token type of that sum. What is sum? Sum is in nothing but an identifier. Okay, so the token type of the sum is identifier. Okay, and is it the first identifier? If yes, then it will write identifier 1 ID, comma 1. If it is second identifier, ID, comma 2. Okay. Since starting, whenever it is scan the program, starting onwards, okay, whenever it encounter an identifier, it assign the identifier with the name of the, it identify the token type of the identifier. What is the token type? That means the name of the identifier along with the numbering of the identifier. Okay. If the identifier is the first one, then the entire token for that identifier will be the name of the identifier, comma, the serial number of the identifier. Identifier 1, identifier 2, like that. Okay. Similarly, assignment is nothing but an operator which is predefined. Here, no more extra token need to be generated. Okay. It is already predefined. A is another identifier. So what type of, it is second identifier. Okay. The second identifier, even though it is identifier, the serial number is second. So here the token type, the entire token will be like this, identifier, comma 2. That means name of the name A indicates A is an identifier and the serial number is 2. That is called as ID2, identifier 2, second identifier. Okay, and then plus is an operator which is predefined. No more things to do. It is just to read. Yes, plus is a predefined symbol which is already defined to the compiler. So no more extra information need to be incorporated for the operator plus. Then 10 is a real number. 10 is an integer number. It is a constant. Okay, the value is already known to the compiler. Okay. So no more extra information need to be acquired or need to be incorporated in the symbol table by the lexical analyzer. Okay. Next, once these are the tokens generated for that single line. These are the tokens generated by the lexical analyzer. Once it is scanned sum, what is sum? Sum is an identifier, and what is the serial number of that identifier? The serial number of that identifier is 1. Okay, identifier comma 1. Or in short, you can write. We have seen previously in the previous example, ID1, ID2, ID3. That 1, 2, 3, the subscripted variable is nothing but the serial number. Very simple. You can just, instead of sum, you can write ID1. Instead of A, you can write ID2. And no more other things to be written there because plus and equal operator 10, these are the predefined symbols, predefined values to the compiler. Okay. These tokens are generated by the lexical analyzer. So the process of generating or identifying token for a particular word or lexeme is called as tokenization. The process of scanning the input symbol character by character, and upon getting a single word, find out the corresponding token type of that word. Okay, find out the corresponding token type of that word. That process is called as tokenization. Very interesting. Okay, very interesting. Once again, let us repeat. Tokenization is the process of scanning the source code character by character. Upon encounter or upon identifying a sequence of characters, that means a single word or a single lexeme. Upon identifying a lexeme or a single word, then find out the corresponding token type or find out the corresponding class of that word. Actually, that word belongs to which class? Okay, what is the token class of that word? That is called as tokenization. Very simple. Okay, and this tokenization, what are the components used here? One is lexeme. Lexeme means sequence of characters. S, U, M together. S cannot be taken within a word. You cannot separate yes, sir. Yes is a S is a lexeme. No, you cannot say that. You cannot divide the word, the characters of a word. Okay. Rather, a set of characters. Set means one element can also be there. Two elements can also be there. Three symbols can also be there. Four characters can also be there. But the question is, when four characters are consecutively there, you need not to break them. Rather, you start scanning from character 1, 2, 3, and 4. Once you encounter four consecutive characters together, as they appear in the source code, that is called as lexeme or word. And for that word, you find out the class of find out the token type of that. Else, ELSE in the C language. What is that? That is one keyword. Keyword is also one token. A is an identifier. Plus, minus. These are all are what? Into. These all are what? Operators. Okay. So there is a very shortcut way to remember tokens. Acha, you just ask yourself what is a program? A program is nothing but a collection of tokens. Nothing you are writing beyond the token. Okay, nothing. Collection of tokens. Now the question is, what are the different types of tokens available? You just tell me what are the different types of token available in C language. There are some around 6 type of tokens available. The very sweetest way to remember, short and sweet way to remember, you remember the name of a chocolate, cookies. Cookies. COOKIS, something like that. Cookies means C for or Kisco. KISSCO. K for this total is tokens. K for keyword, it is a token. I for identifier, another type of token. S for string is a type of token. Another S for special symbol is a kind of token. So kiss, then co, C. C for constant is a kind of token, maybe real constant, maybe integer constant. Then O for operator. Plus, minus, into, modulus, all these all are functions. A percentage, I mean, logical and logical all together known as operators. So there are KISCO, KISSCO, 6 type of tokens available in C language. Apart from that, there is nothing in C language. Or the entire program, any program you write, these programs comes from KISCO. KISCO is nothing but set of tokens. This is the easiest way to remember. Okay. Okay. Anyhow, the major role of this lexical analyzer is tokenization. Tokenization means identify the lexeme and find out the corresponding token type of that lexeme. Okay. Identify the lexeme and find out the corresponding token. Okay. Suppose one person is missing in abroad. What you can do? First, you identify that person. Once that person is, once you catch that person, what you have to do? You find out you find out which country that person is belongs to. Suppose suddenly a missing person is encountered by you in anywhere in the country or abroad. What you have to identify that person? I mean, by knowing his name, passport, everything you identify. Then find out the which country that person is. That is, identify the person and find out his or her corresponding country. That is called as okay. That is the same time. This job is also same. First, identify a word or lexeme, then find out the corresponding class or the corresponding token type of that lexeme. Okay. Here you see sum is an identifier. Okay, you see the table, and equal is an assignment operator. 10 is a number. These all are the lexeme and the corresponding token and their corresponding token. The token of sum is identifier. The token of equal operator is assignment operator. The sum of equals the token of equal symbol is assignment operator, and the token of 10 is a number. 10 is what? What is the meaning of 10? 1 0. 10 is a number. Later, when you navigate it, you can identify whether it is integer number or it is real number. First, it is what is the category of 10? It is a number only. Okay, it is a constant. Okay, next. Now, the question is how this job is performed by lexical analyzer. How lexical analyzer perform tokenization? Is there any particular tools available with lexical analyzer to perform? I mean, starting from the first character of the word and reaching to the last character of the word, there must be some technique associated with that. No, otherwise, how the lexical analyzer can identify yes, is a word. Initial INITIL, initial is a word. Position POSITION, position is a word. How it can identify? Don't you think there must be some techniques associated with lexical analysis in order to scan the word, or in order to scan the word and in order to know, yes, this is a word and that is not a word. So the technique, there are 2 pointers actually. This to identify the lexeme, lexical analyzer uses 2 pointers. One is Lexeme Pointer, okay, LP. In short, that is called as LP. It normally marks the start position of the lexeme. Normally, and the second pointer is forward pointer. It is scan ahead character by character. Actually, what is the concept behind this? Initially, see, this is one pointer, Lexeme pointer. This is forward pointer, LP, FP. Both of them initially pointing to the first character of the first character present in the input buffer, because every program, when you write program and compile the entire program, okay, line by line, it is stored in the input buffer. From the buffer, the 2 pointers are there, they read, okay, and initially both the pointers are point to the starting cell of the buffer. Then LP, the left LP pointer, it marks the start position and it keeps itself constant. Then the next pointer, forward pointer, it moves one by one. First, after scanning the first character, it go to the next cell. It scan the second character. Then it go to the third cell. Scan the third character. Then it goes to the fourth one. Scan the fourth character. And then it goes to the fifth one. Once in fifth one, if the fifth cell is empty, that means a white space is there. Then in between that third, in between the first and fourth, I mean fifth place, how many cells are there? 4 cells. In that, the content of the 4 cells will be taken as a lexeme. So it starts scanning from the first character, and it goes on scanning character by character. Once it encounter the blank space or white space, it stop. And in between Lexeme Pointer and forward pointer, whatever the character sequence of characters found, that sequence of characters treated as a lexeme. And there the job start. Once the lexeme identified, then it find out the token types. What is the class of that lexeme? Okay, that is the concept behind tokenization. Okay, here let us realize how tokenization carried out with the help of LP and forward pointer. LP means Lexeme pointer and FP means forward pointer with the help of an example. You see the down of the screen, one example is given, total equals to marks plus 50. Okay, one expression is given that total equal to marks plus 50. I hope you are understanding, my dear. Yes or no? Very good. I hope you are understanding because I am going through the route actually. Starting from the route, I am telling you the concept. I don't think that any doubt will be there. Still, if you have any doubt, you can send me through comment. Okay. And before that, I would like to tell you if possible, you subscribe and give like as much. I will give like also, like the channel and subscribe the videos. Thank you. Okay, this total equals to marks plus 50. This is an expression given to you. Okay, now this expression, you as a lexical analyzer, you have to read them character by character and find out one sequence of characters, that is one word, and find out the token type of the. Just identify what that word is and what that symbol is. Okay, that is called as tokenization. Okay, now let us see. The very interesting diagram is there. You can see. See, don't already left side part is already discussed. Okay, no more discussion is required of that. But same thing is repeated. Okay, LP lexeme pointer. LP marks the beginning of the current lexeme. Current lexeme means the current word. Points to the first character of the lexeme. Yes, it points to the first character. It remains fixed while a forward pointer scan ahead. Okay, the second pointer moves. Okay, it moves only when the new lexeme start. Yes, first lexeme is identified and the corresponding token type is identified. Then LP will now come here. They will scan the second word. Second word again LP will be constant and forward pointer will keep on moving. Again it encounters space. Then the second word is identified. And then identify then they find out the corresponding token types of the second. In this way, the entire scenario can be formed. Okay, I mean the entire tokenization process is carried. Forward pointer scan the character one by one from the left to right. This is the nature, okay, of the parser. Yeah, it moves forward till it finds the end of the lex. As I said, it will until it find out a white space. White space means end of the first lex. Okay. It may read one extra character called as look ahead. Okay. It stops at delimiter, white space, or invalid character. If any invalid character is found, then it stops. Any white space is found, it stops. Okay. So it helps in recognizing the token type of the lexeme. Okay. Let us take one example, total equal to mark plus 50. Here you see the same thing is written here. Okay. So the same thing is diagrammatically given here. Diagrammatically, let me move this here. You see, total, everything is loaded in the input buffer. The total cell, no, are you seeing that? You can see the entire, this is nothing but your RAM card, a random access memory, which actually holding now, I mean, when you load the program get loaded into the RAM. That is nothing but the buffer. Okay. That buffer means it has number of cells. It consists equal number of cells. I mean, the size of every cell is equal. Okay. So you imagine the total equals to marks plus 60. Okay, marks plus 60. Now imagine that this statement is loaded in the box. Total TOTAL, then space equals to marks plus 60. Let us assume that total is already scanned. Okay, now now the pointers are looking for a new lexeme. Let us say marks. Okay, so you can identify how both the lexemes are working together in order to find out the lexeme called as marks, and in order to find out the corresponding token type of marks. Here you see first LP lexeme pointer is pointed. I mean, it is pointing to M. Mark means MARKS. Okay, 5 characters. So first LP is both the pointers are together. I mean, LP and FP both are earlier point to the character M. Now LP is constant at M, but forward pointer is moving. You see forward pointer. You see just the movement of forward pointer below to the first screen. I mean first half of the screen. Okay, first M, then A, then R, then K, then S. Okay, and then plus. When it encounter plus, okay, that means so M A R K S. When it encounter plus and S, they are not what I mean. They are different symbols, right? So their marks can be taken as a single word. Okay, marks can be taken as a actually here space is there, but in this example space is not mentioned. Okay, actually MARKS, after that space will be there. Once it encounters space, that single word will be called as marks. For that marks, what is mark? Mark is a user defined word. Yes or no? That user defined means it is identifier. So it identify the after delimiter found. After delimiter means a space. Here I mean the example is big, but the number of cells are very less. Okay, because of that complexity, that white space is not mentioned actually, but it is written clearly. You see to the down after delimiter found. Okay, the entire word marks is considered as a lexeme, and the corresponding token type need to be found. What is the corresponding token type? You tell what is mark. You have entered a variable marks. That variable is not predefined. That is user defined. So identify. Okay. So in this way, the lexeme, I mean both the lexeme pointer as well as forward pointer, they works. They perform tokenization. Now another question is coming. Sir, okay, token is identified. Lexeme is identified. You said that any sequence of characters between the lexeme pointer and the forward pointer, okay, the forward pointer is considered as a lexeme. Okay, sir, we understood that. Fine. Then how you identify the corresponding token type of that word or that lexeme? For that, Lexical Analyzer uses a very interesting tool called as Deterministic Finite Automata. Okay, that will be seen in the future classes. Okay, now you see. Yes, here only it is there. Okay. So how exactly it happens? So, okay, you identified something. You got something. Okay, you got something. Suppose, yes, very simple. You got the word. Now the question is how to identify the class of that word. What type of word it is. Whether it is a keyword, whether it is an identifier, whether it is an operator, whether it is a special symbol, whether it is a constant. How, sir? How can you identify it? Or how exactly it happen? Happening. This is happening through a very interesting tool that is used by the compiler that is known as deterministic finite automata. This normally this context the compiler design syllabus is present is available for 3-1 student, whereas 2-2 students for 2-2 second year second semester student, we used to provide a teach the subject called as theory of computation or formal languages and automata theory. Both are same. Okay. So this DFA, deterministic finite automata, is nothing but a prerequisite here to the compiler design. Before we study compiler design, we must know what is deterministic finite automata and what is context-free grammar. Okay, this preliminaries must be with us. Okay, but no problem. I came forward with the definition and the how deterministic finite automata works. Okay, we'll discuss that. Your doubt will be clear. You'll be knowing about the working principle of deterministic finite automata. Then you can easily understand how the mapping, this mapping, knowing from the word to the token, how that mapping is done. For a single word, M-A-R-K, marks, M-A-R-K-S, marks. Sir, you are saying marks is an identifier. How you are saying? Is there any tool? Okay, we know the rule. But how system is doing that? You show us that, sir. Similarly, 101. 101 is nothing but a constant. Sir, what you said, that is correct. It is a constant. But so how the system is identifying that is a constant? Isn't it? Is it a valid question now? Yes. And I'm there to answer it with full clarity. Don't worry. Okay, now the current topic is we need to know what is deterministic finite. Isn't it? Very good. So next here, deterministic finite. So once again, two lines are present here. The lexical analyzer is the first phase of a compiler. It reads the source code character by character. Yes, we agree. We have seen that. Okay, and to recognize tokens efficiently. Okay, to recognize tokens efficiently, the lexical analyzer recognize means you got a word. For that word, you need to identify the token. That is called mapping. Okay, that mapping. For that mapping, it uses a DFA, deterministic finite automation. Okay, deterministic finite automation. Which we have already studied in 2 as I can assume that. But if you have started, I can make you to recall through the help of my slides. Otherwise, if you don't know also, if you pay attention at press also, you can able to know what is DFA and what is the working principle of DFA. Okay, no problem. You can easily understand and you can easily identify what is the actual implementation of DFA in compiler. Okay, so what is a DFA? A deterministic finite automata is a state machine used for pattern recognition. Okay, pattern recognition, pattern, identifying the pattern. Okay, it reads one input character at a time. It changes the state only one state at a time. From the present state to the next state. The next state can also be the old state sometimes. Okay, so it changes the state one state to another based on the transition rule. Okay, when a valid pattern is recognized, the DFA reaches to the final state. Once it reads a sequence of pattern, a valid pattern, then normally whenever it reads input, it jump from one state to the next state. Let us say it is in the starting state. It reads the jump from start state to the next state. Then from there it may reach another symbol. There it may jump to another state. Like that, it can jump randomly. okay, based upon the input, okay. And finally, when all entire input it reads, it may reach to the final state. And if it reaches to final state, then we can say the pattern is okay. The input sequence is okay. Okay. The recognition, the recognized lexeme is then converted into it. Okay. Then once it reach to the final state, starting from the start state, okay, while reading the input symbol, if it reach to the final state, then the entire input pattern is a valid pattern. I mean, is a valid lexeme, and for that, the corresponding token is easily identified. Okay, that we'll be discussing. Yeah, before that, this DFA has several components. Okay, let us understand what are the components, because without this, it will be difficult to understand what is DFA. It has several components like a set of states. Okay, states represent different stages of recognition, jumping from state 1 to state 2 to state 4, state 4 to state 3 to state 1, state 1 to state 0, state 0 to final state. Random. That is called as different stages of recognition. Okay, so it has sequence or set of states. You can ultimately see. Now each state indicates the current condition of scanning. Okay, let us take the example. Q0 is the start state, Q1 is the identifier recognized. Q1 is a state where the machine can recognize the identity. It may be the final state. Okay. Next is transition. What is transition? Transition defines how DFA moves between one state to another state. I mean, how DFA moves between states. Q0 to Q1, Q1 to Q3, Q3 to Q0, Q0 to Q4, Q4 to Q5, Q5 to Q0, again Q0 to final state. How this transition, okay, how the DFA is a transit from one state to another, that is called as the movement of DFA. Okay, transition define how DFA moves between states. Okay, then movement depends on the input character. It solely depends on the input. What input it is consuming. Now I am in state 0. I am consuming some input. I may jump from state 0 to state 1. Okay. Normally you see whenever you are inserting ATM card in the machine, earlier machine is in idle state. Whenever you are inserting ATM card, machine is jumping from idle state to the starting state. Then there it is scanning the ATM card. I mean barcode. If it is correct, then it is going to another state. And there it is asking you or producing you a main menu and asking you to enter the option withdraw, pin change, XYZ things. That is there the states getting changed. Okay. So you need to realize in that way. That is the best example I cited. Okay. Next, later move from Q0 to Q1 digit remain in Q1. It depends on the type of input, whether it is consuming a input as a letter or as a digit. Okay. Then final or accepting state. Final state is a part of the state, also known as accepting state. It is a state that a valid token pattern is recognized. So when it is reached to the final state, then you can say that the job is over and the reading of input is over and the input is valid, and for that the corresponding token is also identified. Okay. When DFA reaches an accepting state and a delimiter is found, the lexeme is accepted. That means the lexeme is valid, and for that the corresponding token is already there. Automatically the mapping is carried out. That I can show you next class. Okay, we will be learning this in depth because very interesting concept, deterministic finite automata, because it is acting as a tool in the compiler in the lexical analyzer. Okay, you must know it thoroughly. Okay, very interesting things, and we have number of examples to go through. Okay, so not to worry. So we will be discussing this in the next class. Okay, from this components of DFA is over. Otherwise, I can start it from this slide onwards, no problem. Okay. So thank you. Have a good day. All the best. Okay, thank you.